There is a number that humanity once found comforting: 93 billion light-years. That was the diameter of the observable universe, the immense but bounded sphere of everything we could, in principle, ever see. It was a number so large it dissolved the mind's ability to hold it, yet it existed. It had been written down. It had been agreed upon. And in some quiet, irrational way, it had become a kind of wall, not a limitation, but a reassurance. A final edge beyond which you could project your imagination without fear of consequences, because nothing out there could touch you. Nothing out there could answer back. The universe was enormous, yes. Incomprehensible, certainly. But it had a size, and things that have a size can be, however imperfectly, understood. And then the James Webb Space Telescope opened its eye, not like a door being opened, more like the moment you realize the room you've been standing in your entire life has no walls, that what you believed were solid boundaries were painted illusions, and beyond them stretches something so vast and so structurally alien to your expectations that the very tools you built to measure it are now measuring their own inadequacy. Webb was launched in December 2021. It reached its destination, a gravitational balance point nearly 1.5 million kilometers from Earth, and began to unfold. 18 hexagonal mirrors coated in gold, a sun shield the size of a tennis court, an instrument capable of seeing the universe not in the visible light your eyes were designed to process, but in infrared, the long, cool wavelengths of ancient light, stretched thin by billions of years of travel across an expanding cosmos. Webb was built to see the earliest things, the first galaxies, the first stars pulling themselves from the primordial dark. It was built to confirm the story we already believed we knew, a universe that started simple, small, and hot, and grew slowly into complexity. What it found instead was a catastrophe of assumptions. The images began arriving in 2022, and scientists, people who had spent careers building the mathematical architecture of the cosmos, began to feel something they rarely admit to feeling: unease. Not the productive unease of a puzzle waiting to be solved, but the deeper, more disorienting unease of a framework beginning to fracture. Because Webb was finding galaxies in the early universe. Galaxies that were massive. Galaxies that were structured. Galaxies that had billions of stars already in organized, mature formations. And they existed at a time when, according to every model we had constructed, there should have been nothing but hydrogen gas and the slow grinding work of gravity just beginning to pull matter together. These galaxies should not have existed yet, and yet there they were. Bright, clear, undeniable, staring back at us from the edge of time. But before we follow that thread, before we walk into what those galaxies mean, what they imply about the size and age and fundamental architecture of everything that exists, you should know that this is not a story about a telescope. Telescopes are instruments. This is a story about what happens when an instrument designed to answer questions begins instead to multiply them. About what it means when the universe, forced to reveal more of itself than ever before, reveals not clarity, but depth. Not conclusions, but caverns. This is a story about the uncomfortable possibility that we have been oriented wrong in the cosmos, that our maps, our models, our most confident equations are describing a universe that is far smaller, far simpler, far less strange than the one actually out there. If that kind of question pulls at something in you, if the intersection of science and vertigo feels like home, stay here. Leave a like, subscribe to this channel, and let's go deeper together. Because what comes next will not leave your perception of reality intact. The observable universe is defined by a simple, brutal constraint: the speed of light. Light travels at approximately 299,792 kilometers per second, the absolute speed limit of the cosmos, the fastest that any information can move through space. The universe is approximately 13.8 billion years old. That means the farthest light that could ever have reached us since the beginning must have been traveling for 13.8 billion years. And so the observable universe, the sphere of everything we can even theoretically detect, has a radius of 13.8 billion light-years. Except it doesn't, because while that light was traveling, Space itself was expanding. The galaxies at the edge of what we can see were not stationary while their light moved toward us. Space carried them outward. The fabric of the universe stretched as the photons moved. And so those galaxies, whose light has been traveling for 13.8 billion years, are now, right now, in this moment, approximately 46 billion light-years away from us. The diameter of the observable universe, then, is not 13.8 billion light-years. It is 93 billion. And the universe beyond the observable, the part that exists but whose light has not had time to reach us, is larger still. How much larger, no one knows. Estimates range from moderately larger to effectively infinite. The honest answer is, we cannot see it, and so we cannot say. This is the first layer of the disorientation Webb forces on you. Because when scientists say, the observable universe, they are already working within a constraint so severe it should collapse your sense of scale entirely. Everything you have ever heard about astronomy, every galaxy, every nebula, every black hole, every supernova, every quasar, exists within a region of space that may be a vanishingly small fraction of what is real. The universe we discuss, the universe we map, the universe we argue about is not the universe. It is the universe's horizon. It is everything we can legally see, like a prisoner allowed to look only through the bars of a window, trying to describe a city from a single square of sky. And into that limited window, Webb pointed its golden mirrors. What it saw in those first extraordinary deep-field images was not the simple early cosmos the models had promised. It saw structure. It saw density. It saw galaxies that looked, in some disturbing ways, more like mature galaxies than infant ones, with defined shapes, organized stellar populations, masses that exceeded what gravity should have been able to accumulate in the short time available since the Big Bang. When astronomers first processed the data, some assumed there were calibration errors. When the errors were ruled out, some assumed unusual astrophysical conditions. But as the months passed and more observations were collected, a quieter, heavier explanation began to circulate in the literature. Maybe the early universe was not as simple as we thought. Maybe the standard cosmological model, the bedrock equation set that has governed our understanding of cosmic evolution for decades, is missing something fundamental, missing something in the equation for everything. That phrase, spoken carefully between cosmologists in seminars and papers, is the scientific equivalent of looking down and realizing the floor has disappeared. It does not mean the model is wrong about everything. It means the model may be wrong about something deep, something structural, and we do not yet know what it is. We do not know which assumption to question first. We do not know where the fracture begins. All we know is that the universe Webb is showing us does not quite match the universe we calculated. And in science, when the universe disagrees with the calculation, it is never the universe that made a mistake. The picture Webb sent back of the galaxy cluster SMACS 0723, released to the world on July 12, 2022, showed thousands of galaxies in a sliver of sky so small that, held at arm's length, a grain of sand would cover it. Thousands of galaxies in a grain of sand's worth of sky. And that image was not special. It was not a region selected for its density. It was simply where Webb happened to look. Any direction you point the telescope reveals the same abundance. The cosmos is filled, in every direction, with more galaxies than every grain of sand on every beach on Earth. And within that incomprehensible abundance, Webb found the anomalies, the impossible galaxies, the early structures, the things that weren't supposed to be there. The wall of 93 billion light-years had not disappeared. But something worse had happened. It had stopped feeling like a wall. It had started feeling like a keyhole, a narrow, accidental aperture through which we were peering into something so much larger that the distance between the wall and infinity had effectively collapsed. The number was still there, but the comfort it once offered was gone. And where comfort ends, the real questions begin. Try, for a moment, to hold a single light-year in your mind. Not the full 93 billion. Just one. A single light-year. The distance light travels in a full year, moving at nearly 300,000 kilometers every second, never slowing, never resting, crossing space without friction or resistance. In 1 second, that light could circle the Earth 7.5 times. In 8 minutes, it reaches the Sun. In 4 years, it reaches the nearest star. In 1 full year of relentless, uninterrupted travel, a year in which you were born, grew, changed, maybe fell in love, certainly forgot things and learned others, watched seasons turn and clocks advance. Light covers approximately 946 trillion kilometers. That is 1 light year. 1 unit on the map of the cosmos. The smallest useful ruler we have for measuring the distances between stars. The nearest star to our Sun is Proxima Centauri, 424 light-years away. The Milky Way, the galaxy you live inside, stretches roughly 100,000 light-years across. That means, traveling at the speed of light, the physical maximum, the hardest ceiling the universe imposes on anything, it would take your great-great-great-grandchildren's great-great-great-grandchildren, and then 10,000 generations of their descendants, to cross the galaxy you are part of. Not the observable universe, not even one of the 2 trillion other galaxies in it, just the one you already inhabit. Now hold that. Hold the 100,000 light-years of the Milky Way as your new unit of measurement. Call it 1 galaxy width, and consider that the observable universe contains roughly 2 trillion galaxies, 2,000, $1,000, each separated from its neighbors by millions of light-years of empty, expanding void. The average distance between galaxies in our local neighborhood is about 2.5 million light-years. That is 25 Milky Ways of empty space, stacked end to end between us and the Andromeda Galaxy, our nearest large neighbor. And Andromeda is, by cosmic standards, essentially next door. You are beginning to feel it now, the weight of this. The way the numbers refuse to stay in your mind as numbers and instead start pressing on something more instinctual. The thing inside you that understands distance as something walked, something felt in muscle and fatigue. The mind evolved to navigate a savanna. It evolved to gauge distances measured in minutes of walking, hours of travel. When the universe asks it to comprehend 1 trillion kilometers as a single step in a journey of 46 billion such steps, something behind the eyes quietly begins to fail. This failure is not ignorance. It is the honest recognition that certain scales exist beyond the reach of intuitive comprehension, accessible only through mathematics, and even then, only as symbols, as agreed-upon abstractions with no sensory counterpart. This is what makes Webb's images so destabilizing. They give the incomprehensible a face. When you look at the Webb deep field, that single grain of sand sliver of sky crowded with galaxies, you are not seeing an abstraction. You are seeing light. Actual photons that left their sources millions or billions of years ago, traveled across an expanding universe, entered Earth's atmosphere, bounced off a gold-coated mirror in space, were converted into data, transmitted across the void back to Earth, processed, color-corrected, and placed in front of your eyes. Every smudge of light in that image is a galaxy containing hundreds of billions of stars. Every one of those stars is, in some sense, a sun. Every sun may harbor worlds. And every one of those galaxies, all the thousands of them visible in a patch of sky a grain of sand could cover, is separated from every other by millions of years of light travel. You are looking at a picture, and the picture contains more suns than there are grains of sand on Earth. And this is just what fits in 1 grain of the sky. Now consider what this means for the earliest images Webb has captured. When you look at something far away, you are not just seeing across distance, you are seeing across time. Light has a finite speed, and the universe is not courteous about this. It does not pause and wait for you to catch up. A photon leaving a galaxy 10 billion light-years away carries with it the image of that galaxy as it was 10 billion years ago when it emitted that light. By the time those photons reach Webb's mirrors, 10 billion years have passed. The galaxy has evolved. Stars have lived and died within it. Entire stellar populations have burned out and been replaced. What you see in the image is not where that galaxy is. It is where it was. You are not seeing the universe. You are seeing the universe's past. This is not metaphor. This is physics. Every image is an archaeology. Every telescope is a time machine. The farther you look, the older the light, and the deeper into the past you are forced to peer. When Webb captures galaxies in the first few 100 million years after the Big Bang, it is doing something that no other instrument in history has managed at that resolution. It is showing us the actual face of the young universe. Not a simulation, not a projection, the real thing. Photons that were emitted when the cosmos was still an infant, crossing all of time and space to fall at last onto a mirror built in a factory in Maryland and launched into space by human hands. There is something almost unbearable about that. Something that ought to stop you for a moment and refuse to let you treat it as ordinary information. And what does the young universe look like in Webb's images? That is where things become strange. Because according to the standard model of cosmology, the LCDM model, lambda cold dark matter, the mathematical framework that has governed our understanding of the universe's evolution for 30 years, the early cosmos should look simple, young, unformed. Structure should grow slowly, hierarchically, from small things to large. First individual stars, then small clusters, then dwarf galaxies, then large galaxies, then galaxy clusters, then the vast cosmic web of filaments and voids that defines the large-scale architecture of the universe today. This process takes billions of years. Gravity is patient but not fast, and so in the earliest moments Webb can see, we expected to find chaos. Proto-galaxies struggling to coalesce, gas clouds only beginning their first contractions. What we found instead were galaxies that looked like they had already finished growing. Massive, red-quenched galaxies, meaning galaxies whose star formation had already slowed or stopped, appearing at redshifts so high they correspond to the first billion years of the universe's existence. Galaxies with stellar masses that, according to the models, should have required several more billion years to accumulate. Not one of them, not two, a statistically significant population, appearing again and again across different Webb observations, in different parts of the sky, consistent enough that they could not be dismissed as local anomalies or measurement errors. Astronomers began calling them, informally, impossible galaxies. The name was half joking, but only half. Because what these galaxies imply is not just a gap in the model, a missing ingredient, a parameter that needs slight adjustment. What they imply, if they hold up to continued scrutiny, is a fundamental revision of how we understand cosmic structure formation. Either the early universe was denser than we thought, with regions of matter concentrated enough to form massive galaxies faster than current physics allows, or there are processes at work, star formation efficiencies, dark matter dynamics, feedback mechanisms, that our models simply do not account for. Or, and this is the possibility that makes cosmologists go quiet at conferences, the model itself is built on assumptions about the universe's history that may not be fully correct. The age of the universe, the rate of expansion, the nature of dark matter, the mechanics of inflation. These are not small things to question. They are the load-bearing walls of the cosmological house. And Webb is pressing on them, gently but persistently, the way water presses on a structure not quite sealed against the flood. Every week, new data arrives. Every month, new papers. And in those papers, carefully worded, densely footnoted, peer-reviewed and cautious, a quiet alarm is ringing. Not loudly, not with drama, but persistently. The universe is not what we thought it was in its earliest moments. And if the beginning was different, if the architecture of the young cosmos was denser, more structured, more abundant than our equations allow, then everything that followed from that beginning may need to be reconsidered. You have been measuring the universe with a ruler. Webb has just shown you that the ruler may be too short. And the question is no longer how much longer the ruler needs to be. The question is whether the concept of a ruler was ever the right tool to begin with. To understand how strange the Webb findings truly are, you need to understand what was supposed to happen at the beginning. Not the very beginning, not the first fraction of a second, the quantum foam, the singularity and its unknowable physics. Start a little later. Start at the moment, roughly 380,000 years after the Big Bang, when the universe cooled enough for electrons to bind to protons, and the cosmos became, for the first time, transparent. Before that moment, the universe was a plasma, a hot, opaque fog of charged particles through which light could not travel. After it, the fog cleared. Light moved freely for the first time, and that first light, stretched by 13.8 billion years of cosmic expansion into the microwave range, is what we detect today as the cosmic microwave background, the faint, nearly perfectly uniform glow that fills the entire sky, the oldest light we can ever observe, the literal image of the universe at 380,000 years old. That CMB image is almost perfectly smooth. There are tiny variations, fluctuations in temperature and density at the level of 1 part in 100,000, but they are small. The young universe, as revealed by its oldest light, was extraordinarily uniform. Matter was distributed almost evenly across space. There were no galaxies, no stars, no structures of any meaningful scale. Just a nearly featureless sea of hydrogen and helium, with faint ripples of slightly higher and lower density that gravity, over billions of years, would slowly amplify into the cosmic web we see today. This is the foundation of the standard model of structure formation. It is elegant, it is mathematically powerful, and it makes a very specific prediction. Complexity takes time. Large structures emerge late. The universe builds from the bottom up, small things first, big things later. A galaxy like the Milky Way, with its hundreds of billions of stars, its central bar, its spiral arms, its orbiting satellite galaxies, required billions of years to assemble. The models say so, the simulations say so, the entire theoretical framework of modern cosmology says so. And then Webb looked at the universe when it was 500 million years old, less than 4% of its current age, and found galaxies that, by the models, had no right to be there. Not small galaxies, not simple embryonic clusters of stars struggling to hold themselves together. Massive, evolved, recognizable galaxies, with stellar populations that implied they had been forming stars at extraordinary rates for hundreds of millions of years before the moment Webb captured them. One galaxy in particular, catalogued as JADES GS Z130, was confirmed to exist just 320 million years after the Big Bang. 320 million years. In cosmic terms, that is the blink of an eye. The sun has been burning for 15 times longer than the entire age of the universe at that moment, and yet there was a galaxy. Structured, luminous, already ancient in some sense relative to the time available for it to have formed. When astronomers calculated the stellar mass of these early galaxies, the total amount of matter that had already been converted into stars, they found numbers that broke the models. To accumulate that much stellar mass in that little time, those galaxies would have had to convert gas into stars with an efficiency that exceeds anything current physics considers possible. Under standard conditions, only a small fraction of a gas cloud's mass ends up in stars. Most of the material is blown away by stellar radiation and supernova winds before it can collapse. But the early universe, if Webb's data is correct, was producing stars at a rate close to 100% efficiency in some regions. Every molecule of available gas turning into stars. No waste, no dispersal, an almost impossible thermodynamic concentration of stellar birth. Or, and here is where the vertigo truly begins, the standard conditions were not standard at all in the early universe. The initial conditions were different from what we assumed. The density fluctuations in the CMB were not the whole story. There were seeds of structure in the early cosmos that our current models do not account for. Seeds that allowed gravity to win faster, to pull more matter together sooner, to build galaxies before they were supposed to exist. What could those seeds be? There are proposals. Primordial black holes. Black holes that formed not from collapsing stars but directly from the density of the early universe, potentially providing gravitational anchors around which matter could accumulate far faster than the models allow. There are suggestions of modified gravity, of exotic dark matter interactions, of early dark energy fluctuations. None of these proposals is confirmed. All of them require revising something that was previously considered settled, and each revision pulls on other threads, threatening to unravel adjacent pieces of the framework. Consider what hangs on the standard model being right. The age of the universe, 13.8 billion years, is derived from that model. The rate of cosmic expansion, measured through the Hubble constant, depends on that model. The proportion of matter, dark matter, and dark energy in the universe. The famous 5%, 27%, 68% breakdown is inferred through that model. If the model's treatment of structure formation is fundamentally flawed, the entire calibration of the cosmos may need adjustment. Not the small adjustments of fine-tuning, the kind of adjustments cosmologists make routinely as new data arrives, but foundational adjustments, adjustments to the equations themselves. This is not how science usually feels from the outside. From the outside, science looks like a process of accumulation, each generation adding more bricks to the same building. But from the inside, from the position of a cosmologist reading Webb's data in 2023 or 2024, it can feel like something else entirely. It can feel like finding, buried in the foundation of the building you've been adding bricks to for 30 years, a crack that runs all the way down. Not every scientist believes the crack is structural. Many are cautious, conservative, appropriately skeptical. They point out that measuring the masses and ages of distant galaxies is extraordinarily difficult. The uncertainties are large, the techniques are still being refined, and Webb's data is still young. Give it time, they say. Give it peer review, replication, calibration. The impossible galaxies may turn out to be merely improbable. The model may bend, adjust, absorb the new data without breaking. But others, a quieter, more unsettled group, are not so sure. They look at the sheer number of anomalous detections. They look at the consistency of the excess across different fields of view, different observational techniques, different research teams working independently. And they allow themselves to wonder, carefully and professionally, whether Webb is doing something more than discovering new data points, whether it is instead revealing a new universe, a universe that was not simpler in its youth, but stranger, a universe that did not build structure slowly, patiently, from the bottom up, but which erupted into complexity almost immediately, as if the conditions at the beginning were tuned, loaded, primed for rapid structure formation in ways we have not yet understood, as if the cosmos had been waiting, coiled, for the first signal to release. And this is where the scale problem truly begins to compound itself. Because if the early universe was more structured than we thought, if it produced more galaxies, more stars, more heavy elements, more complexity in its first billion years than our models allow, then the universe is not just larger in space than we imagined. It is larger in time, richer in its history, fuller in its past. The story we thought we knew, the story of a cosmos slowly waking from primordial simplicity, may be wrong. And the real story, the actual history of everything that exists, may be both more ancient and more intricate than anything we have yet been able to write. The model is not dead, but it is bleeding. And what is bleeding out of it slowly, image by image, dataset by dataset, is the illusion that we understood the beginning. There is a crisis in cosmology that most people have never heard of. It does not make headlines in the way that particle accelerator results do, or Mars landing footage, or the first photographs of a black hole. It lives in the technical literature, in conference proceedings, in the careful hedged language of papers whose abstracts hide a tremor of genuine alarm behind their professional composure. It is called the Hubble tension, and it is quietly one of the most disturbing unresolved problems in all of modern science. Here is the problem. There are two independent ways to measure how fast the universe is currently expanding. To measure the Hubble constant, the number that describes the rate at which space stretches between any 2 points in the cosmos. The first method looks at the early universe. It takes the temperature fluctuations in the cosmic microwave background, feeds them into the standard cosmological model, and extrapolates forward to calculate what the expansion rate should be today. The second method looks at the present universe directly. It measures the distances and recession velocities of nearby galaxies using standard candles, objects whose intrinsic brightness is known, so that their apparent dimness tells you exactly how far away they are. Both methods are careful. Both methods have been refined over decades. Both methods use independent datasets and independent teams of researchers working with independent instruments. And they disagree, not by a rounding error, not by an amount that can be absorbed into the normal uncertainties of measurement. The two values of the Hubble constant differ by approximately 9%, a gap so large, so persistent, and so resistant to every attempted explanation that most cosmologists have stopped believing it will simply go away with better data. The early universe method gives a value of about 67 kilometers per second per megaparsec. The late universe method gives about 73. The difference between them represents an expansion rate that, compounded over 13.8 billion years, implies a universe that is measurably different in its current size and structure, depending on which measuring stick you use. This is not a footnote. This is a fissure running through the heart of the standard cosmological model. And Webb has made it worse, because Webb has independently confirmed the late universe measurements with unprecedented precision. Its infrared capabilities allowed it to measure the distance ladder, the chain of standard candles that connects nearby objects to distant ones, with an accuracy no previous telescope could match. And its results did not bring the two Hubble values closer together. They confirmed the tension. The gap persists. The universe, as measured from the present, is expanding faster than the universe, as predicted from the past should be, which means one of two things. Either both measurement methods are wrong in precisely the same way, a coincidence so unlikely that it would itself require a breathtaking explanation, or the standard model is missing something that affects the expansion history of the universe, something between the early cosmos and the present that we have not accounted for, something that gave space an extra push, an additional acceleration, an energy injection that our equations do not contain. The most obvious candidate is dark energy, the enigmatic component that makes up roughly 68% of the total energy content of the universe and is responsible for the accelerating expansion we have observed since the 1990s. But dark energy, in the standard model, is treated as a constant, the cosmological constant, lambda, a fixed energy density of empty space that does not change over time. If the Hubble tension is real, dark energy may not be constant. It may evolve. It may behave differently at different epochs of cosmic history, more powerful in the early universe than later, or the reverse, or varying in complex ways that no current theory adequately describes. And here is where the terror of the unknown becomes structural. Because dark energy is not a thing anyone has ever directly detected. It is an inference, a number inserted into the equations to make them match the observations. We know it exists in the same way you know there is wind by watching a tree bend, not by touching the wind, but by its effects on everything else. If dark energy is not constant, if it changes over time, we do not merely need a new parameter in our model. We need a new theory of what empty space is. We need a new understanding of why the universe exists in the state it is in, rather than some other state. We need, in the deepest sense, a new physics. And dark energy is only one problem, because alongside the Hubble tension, Webb's findings about impossible galaxies carry an implied companion. If structure formed faster in the early universe than the models allow, then dark matter, the invisible component that makes up 27% of the universe's mass energy content and which supposedly provides the gravitational scaffolding on which galaxies form, may not behave the way we have modeled it. Cold dark matter, the standard assumption, moves slowly in clumps on small scales first, building large structures hierarchically over time. If galaxies were massive and organized far earlier than cold dark matter allows, either dark matter is something else, warmer, more reactive, interacting with itself or with ordinary matter in ways not yet understood, or there is additional structure in the very early universe, perhaps imprinted during cosmic inflation, that seeded the rapid formation we now observe. Inflation itself, the proposed period of exponential expansion in the first tiny fraction of a second after the Big Bang, postulated to explain the universe's remarkable flatness and uniformity, is a theory so fast and so brief that it left barely any direct observational fingerprints. We have never confirmed it. We have supporting evidence, suggestive evidence, circumstantial evidence. But inflation as a physical process remains largely unconstrained. We do not know what drove it. We do not know how it ended. We do not know what it would look like if it had varied across different regions of space, seeding some areas with more density than others. What this means, put plainly, is that the three pillars of the standard cosmological model, dark matter, dark energy, and inflation, are all simultaneously under pressure. Not broken, not disproven, but stressed, strained, being pushed by Webb's observations into configurations where the comfortable old answers no longer fit perfectly and the new answers have not yet arrived. This is the true paradox at the center of what Webb is revealing. It is not merely that the universe is larger than we thought, or older in its complexity, or richer in its early structures. It is that the more precisely we look, the more our measurement systems contradict each other. The more data we collect, the wider the gaps between our predictions and our observations. We are not approaching a unified picture of the cosmos with each new telescope. We are, in some crucial ways, moving away from it. Each answer Webb provides opens a new question. Each confirmation reveals a new inconsistency. We are, as a civilization of curious minds pointed at the sky with the best instruments ever built, discovering that we are less certain about the fundamental nature of reality than we were before we looked this carefully. That is not defeat. Science has always worked this way. Periods of confident frameworks interrupted by crises that force deeper theories. Newton was not wrong until Einstein showed a more complete truth. Einstein's general relativity is not wrong, but quantum mechanics shows its boundaries. The standard cosmological model may not be wrong in its entirety, but it is almost certainly incomplete, and the incompleteness is not a gap at the edges, a missing detail in some obscure corner of the theory. The incompleteness is in the center. In the nature of the most abundant things in the universe, the dark matter and dark energy that together make up 95% of everything that exists, and in the mechanism by which structure first appeared. We have named the darkness. We have given it percentages, symbols, equations, but we have not understood it. And Webb, more than any other instrument in history, is making that lack of understanding impossible to ignore. You are living in the moment when the universe stopped being a solved problem. You may not have noticed. But this is that moment. To understand what Webb is truly measuring, to feel the full weight of what it means to see light that has been traveling for 13 billion years, you need to understand what happens to that light on its journey. Because the light does not simply travel, it is transformed. And the nature of that transformation is one of the most profound, counterintuitive, and quietly devastating facts about the universe we inhabit. When a galaxy in the early universe emits light, that light begins its journey with a specific wavelength, a specific color, a specific energy. Ultraviolet, perhaps, or visible blue, the signature of hot young stars burning through their fuel in the first explosive centuries of a galaxy's life. That light leaves the galaxy and begins crossing space. But space, while the light travels, is not still. Space expands. The fabric of the cosmos stretches, and as it stretches, the wavelength of every photon moving through it stretches with it. The light is not Doppler shifted the way sound shifts when a train passes. That would require movement through space. This is something different. This is the stretching of space itself, carrying the wavelength along, elongating it the way a drawing on a rubber band elongates when you pull the band. By the time that light reaches Webb's mirrors, its wavelength has been stretched from ultraviolet into infrared, from the energetic blue of young stars into the cool, long waves that carry heat signatures. The universe has redshifted the light. It has aged it in transit. This is why Webb was built with infrared detectors. Hubble saw invisible and near-infrared light. It could see relatively nearby galaxies and moderately distant ones, but the most ancient light, the light from the universe's first billion years, arrived at Earth already stretched far beyond Hubble's range. Webb's detectors were designed specifically to catch what Hubble could not, the heavily redshifted light of the universe's earliest structures. And this is also why Webb's discoveries are so unambiguous about the age of the galaxies it finds. The degree of redshift is a precise measurement of distance, and therefore of time. When astronomers assign a galaxy a redshift of Zi10, or Zi13, or Zi16, they are not estimating. They are reading the light's autobiography. They are measuring, in the wavelength of each arriving photon, exactly how much space expanded during the journey. The number is precise. The implications are inescapable. What it means to see a galaxy at redshift Zi13 is this. You are seeing an object whose light left it when the universe was approximately 330 million years old. The universe has since expanded by a factor of 14. Every distance, every structure, every gap between galaxies that existed when that light departed has been stretched to 14 times its original size. The galaxy itself may no longer exist in anything like the form you are seeing. It has had 13.47 billion years to evolve, merge with neighbors, be torn apart by interactions, collapse, flare as a quasar, quiet down, grow a supermassive black hole at its center, and become something unrecognizable. What you see in the image is a relic, a fossil of light, a portrait of something as it was, not as it is. And yet the portrait is real, the data is real, the stellar masses are real, derived from the spectrum of the light, the specific pattern of wavelengths that tells astronomers not just the distance, but the temperature, composition, and age of the stars within the galaxy. When Webb measures an impossible galaxy and finds it contains tens of billions of solar masses worth of stars already formed at 500 million years after the Big Bang, that measurement comes not from a single data point but from a full spectroscopic analysis, the decomposition of the galaxy's light into its constituent wavelengths, each wavelength a signature of a specific physical process, a specific element, a specific temperature regime. The analysis is not simple, but it is not guesswork. It is chemistry read from light, physics extracted from photons, the universe's own record of itself, arriving after a journey of incomprehensible length and duration. This is what makes the anomalies so difficult to dismiss. It would be easy, and initially some astronomers tried, to attribute the impossible galaxies to photometric errors. Early Webb observations used photometry, measuring the total brightness of an object across several wavelength bands and inferring its redshift from the pattern of brightness variations. Photometric redshifts can be wrong. Nearby objects can masquerade as distant ones if their colors happen to mimic the signature of high redshift sources. But as Webb has operated longer, many of the most extreme early galaxies have received spectroscopic follow-up, the more rigorous technique in which the object's light is spread into a detailed spectrum and individual emission lines are identified and measured. Spectroscopic redshifts are nearly impossible to fake. The lines are where the physics says they must be, or they are not there at all. And for a growing number of impossible galaxies, the spectroscopic redshifts confirm the photometric ones. The galaxies are where the data says they are. They are as old as the light claims. The mechanisms behind their existence remain unresolved, but the existence itself is no longer in serious doubt. What astronomers have begun exploring, with a mixture of theoretical creativity and professional anxiety, is the range of physical scenarios that could explain rapid early galaxy formation without completely abandoning the standard model. One direction involves the initial mass function, the distribution of stellar masses within a young galaxy. In the early universe, the gas was hotter, denser, and deficient in heavy elements. These conditions may have favored the formation of extraordinarily massive stars. Stars tens or even hundreds of times more massive than the Sun, burning so intensely that they lived only a few million years before exploding as supernovae and seeding their surroundings with the first heavy elements. A population of these so-called population 3 stars, the theorized first generation, never yet directly observed, could have converted gas into stellar mass at rates far higher than anything seen today, and could have driven the rapid assembly of early galaxies in ways that current simulations, built on assumptions derived from present-day star formation, simply do not capture. Webb is actively searching for population 3 stars. It has not yet definitively confirmed them, but it has found candidates, regions of early galaxies whose spectra show anomalously strong helium emission and almost no trace of elements heavier than hydrogen and helium, exactly what you would expect from a stellar population composed entirely of first-generation stars burning on pristine primordial gas. These candidates are tentative. The confirmation of even one genuine population 3 star cluster would be a discovery of historic magnitude. The first direct observation of the universe's first light sources, the literal original stars, the fires that ended what cosmologists call the cosmic dark ages. The cosmic dark ages. That phrase deserves a moment of reflection. After the CMB was released, after the fog of the early plasma cleared and light could travel freely, the universe entered a period of darkness. There were no stars yet, no galaxies, no sources of light. For perhaps 200 million years, a span of time longer than the entire period from the extinction of the dinosaurs to today, repeated roughly 30 times, the universe was dark. Not the darkness of a room at night, where your eyes strain to find ambient light from distant sources. Absolute darkness. A darkness with no exceptions, no gradations, no points of light anywhere in a cosmos already hundreds of millions of light years across. Hydrogen and helium, cooling slowly, drifting together under gravity's patient pull, with nothing to illuminate them and nothing yet burning to push them apart. And then the first star ignited. We do not know exactly when. We do not know exactly where. We do not know how large it was, how long it burned, what happened when it died. We have never seen one. Every population 3 star that ever existed is long dead, exploded billions of years ago, its material scattered into the gas clouds that became the next generation of stars. But the universe they created, the ultraviolet radiation that ionized the surrounding hydrogen, the heavy elements that seeded the next generation's chemistry, the supernova shockwaves that triggered further collapse and further star formation. All of that cascading consequence is still here. It is in you. Every carbon atom in your body was forged inside a star. Every oxygen atom you breathe, every iron atom in your blood, all of it was processed through stellar interiors and expelled by stellar deaths before it ever became part of a planet, a molecule, a cell, a thought. You are not watching the stars from a distance. You are made of them. You are the universe observing its own past through instruments built from the ashes of its first fires. Webb is not just looking for the beginning of galaxies. It is looking, in some deep sense, for the origin of the matter that makes you possible, for the moment when the dark universe first lit itself, set off the chain of events that would, billions of years later, produce a species capable of building a telescope golden enough to see back to that first light. That chain did not have to work. Every step in it was contingent. Every star that needed to explode to release its elements, every supernova that needed to happen at the right time in the right place, every solar nebula that needed to condense and cool in exactly the right way. All of it was a sequence of events so statistically precarious that its occurrence strains the boundary between physics and something harder to name. And yet here you are, looking back. There is a question that hides inside the Hubble tension, inside the impossible galaxies, inside every anomaly Webb has surfaced, a question that most cosmologists acknowledge but few linger on publicly, because it leads somewhere profoundly uncomfortable. The question is this: what if the universe is not just bigger than we measured, or more structured than we modeled, but fundamentally different in its geometry from what we have assumed? The standard model of cosmology operates on an assumption so basic, so deeply embedded in the framework, that it rarely appears explicitly in papers about galaxy formation or dark energy. It is called the cosmological principle, and it states that the universe, on large enough scales, is homogeneous and isotropic, that matter is distributed roughly uniformly in every direction, and that the universe looks approximately the same from every vantage point within it. This is not a trivial assumption. It is the assumption that makes cosmology possible as a science. Without it, the equations that describe the universe's evolution become so complex as to be unsolvable. The cosmological principle is the simplification that allows the math to work. And there is growing evidence that it may not be entirely true. The largest structures in the observable universe, the cosmic web of galaxy filaments, walls and voids that makes up the large-scale architecture of space, were expected to become featureless and uniform on scales above roughly 300 million light-years. Below that scale, there are structures, clusters, superclusters, filaments, the great cosmic walls of galaxies separated by vast empty voids. But above 300 million light-years, the model predicts, everything averages out. The universe becomes a smooth, homogeneous distribution of matter, and the cosmological principle holds. but observations have repeatedly found structures larger than this. The Sloan Great Wall, discovered in 2003, 1.4 billion light-years long. The Hercules Corona Borealis Great Wall, identified in 2013, roughly 10 billion light-years across. 10 billion. A structure so large that light, traveling at its maximum speed across the entirety of cosmic history, would not have had time to cross it. And yet it appears to exist as a coherent overdensity of matter, a single feature in the universe's fabric larger than the model says any feature should ever be able to form. If these structures are real, if the largest ones hold up to continued scrutiny, the cosmological principle may need to be revised. The universe may be lumpy in ways it should not be, structured in ways that emerge from initial conditions more varied, more complex, more spatially non-uniform than the smooth, nearly featureless CMB suggests. And if the cosmological principle fails on large scales, the equations that describe cosmic expansion, the Friedmann equations, the backbone of all modern cosmology, may be applying a symmetry to a universe that does not possess it. This is not a small revision. It would mean that the expansion rate we measured depends not just on the age of the universe, but on where in the universe you measure it. That the Hubble constant is not a constant at all, but a local value, the expansion rate in our particular region of the cosmos, which may differ from the expansion rate in a denser filament on the other side of the observable universe, or in one of the great voids that appear to occupy a significant fraction of cosmic volume. It would mean that our position in the universe, our address in the cosmic web, is not a neutral vantage point from which we observe an average universe, but a specific particular location that colors every measurement we make. We live inside a galaxy that sits inside a galaxy group that sits inside a supercluster called Laniakea, which stretches across 520 million light-years of space and contains the mass of 100 million billion suns. Laniakea itself sits in a region of the universe that appears to be adjacent to a particularly large supervoid, the KBC void, a region of space with significantly lower than average matter density stretching for more than 1 billion light-years. Some cosmologists have proposed that our position inside or near this void may be part of what drives the Hubble tension. A locally underdense environment could cause the matter around us to flow outward in a way that makes the local expansion rate appear higher than the global average calculated from the CMB. We may, in other words, be misreading the universe in part because of where we stand inside it. Our measurements are not wrong exactly, but they are local. They are the measurements of observers embedded in a specific, non-average region of a cosmos that is not as uniform as we assumed. We are not at the center of the universe. That idea was discarded centuries ago. But we may be in a particularly misleading neighborhood, a region whose local properties we have been inadvertently projecting onto the whole. This possibility, that our cosmic address biases our cosmology, is deeply unsettling in a way that goes beyond the technical. It attacks not just the model, but the premise of the model. The hope of cosmology has always been to transcend the local, to rise above the particular, to describe the universe as a whole from the vantage point of physics, which knows no preferred location. But physics is always practiced from somewhere. Telescopes are always pointed from a specific place. Data is always interpreted through models built by observers who exist in one particular corner of a cosmos they can never fully see. And if that corner is not representative, if the universe does not in fact average out the way we assumed, then every cosmological conclusion we have drawn from our position may carry a systematic error we cannot fully correct for, because correcting for it would require standing somewhere else, and there is nowhere else we can stand. Webb compounds this problem in a specific and haunting way, because Webb is not merely confirming that distant galaxies exist, it is measuring their properties in ways that depend critically on the accuracy of our distance measurements. And distance measurements depend on the Hubble constant, which is in tension, which may vary across the universe, which means that every distance Webb measures, and therefore every age, every mass, every luminosity it derives for every galaxy it observes, carries within it the unresolved uncertainty of the Hubble tension. The impossible galaxies may be partly impossible because we are measuring their distances with a ruler whose length we do not know precisely. Correct the ruler, and some of the impossibility may resolve, but the Hubble tension will not correct itself without new physics. And until new physics arrives, every measurement Webb makes rests on a foundation with a known crack in it. There is something almost vertiginous about this layering of uncertainties. Not the comfortable uncertainty of a problem that is difficult but tractable, where you know what you do not know and can map the path toward knowing it. This is a deeper uncertainty. The uncertainty of not knowing which of your tools is miscalibrated, which of your assumptions is wrong, which of your foundational choices led you to a framework that fits most of the data but cannot fit all of it. It is the uncertainty of a cartographer who realizes, halfway through mapping an ocean, that the compass they have been using drifts in this particular latitude, and they do not know by how much. The ocean is still real. The map is still mostly correct. But the most distant shores, the most extreme reaches of what Webb can see, are drawn with a hand that may be slightly off, in a direction and by an amount that remains for now unknown. And beyond the technical, there is a human dimension to all of this that science rarely pauses to acknowledge. Every researcher who has spent a career on the standard cosmological model, who built their expertise on its framework, who published hundreds of papers using its assumptions, every one of them is now sitting with data that refuses to fully cooperate. This is not a comfortable experience. It is not the clean, triumphant feeling of discovery that popular accounts of science celebrate. It is the quietly disorienting experience of realizing that the map you drew with extraordinary care may need to be redrawn, that the certainty you projected into your equations has encountered a universe that is, in at least some ways, more complex and less cooperative than you accounted for. Science survives this. It always has. The history of physics is a history of frameworks that were almost right, that worked brilliantly within their domain, and that eventually met the observation that exceeded their reach. Newton met Mercury's orbit. Classical electrodynamics met the photoelectric effect. The steady-state universe met the CMB. Every breaking point produced a deeper theory. The standard cosmological model, if it breaks, will break towards something richer, something that contains it as a special case and reaches further into the darkness. But we are not at the new theory yet. We are at the breaking point. We are at the place where the data no longer fully fits, and the replacement has not yet arrived. We are in the uncomfortable interval between one framework and the next. And Webb is the instrument that has placed us here, not by failing, but by succeeding beyond what any previous telescope dared to see. Every answer it finds is a door into a larger room, and every larger room has more doors than the last. Silence is not the absence of something. In the universe, silence is a fact that requires explanation. Consider what Webb has given us. 2 trillion galaxies in the observable universe alone, each galaxy containing, on average, hundreds of billions of stars. Many of those stars, we now know, host planetary systems. The Kepler Space Telescope surveyed a small patch of sky and found planets so abundantly that astronomers revised their estimates sharply upward, concluding that most stars likely have planets, that rocky planets in the habitable zone are common rather than exceptional, and that the sheer number of worlds capable of supporting liquid water and complex chemistry is, by any reasonable calculation, staggering. And Webb has pushed this further. It has detected water vapor, carbon dioxide, methane, and other molecules of biological relevance in the atmospheres of exoplanets dozens of light years away. It has found the chemical precursors of life drifting in the cold gas clouds between stars. It has shown that the raw materials of biology are not rare. They are scattered across the cosmos with the same casual abundance as hydrogen. Now add time. The universe is 13.8 billion years old. Life on Earth required approximately 4 billion years to produce a civilization capable of building telescopes. But Webb has shown us that galaxies were forming within the first few 100 million years. That means stars have been burning for nearly the entirety of cosmic history. That means planetary systems around those early stars have had, in some cases, 10 or 12 billion years longer than Earth to develop whatever chemistry, whatever self-replication, whatever complexity the laws of physics allow. 10 billion additional years, a span of time so incomprehensible that reducing it to numbers does it no justice. It is better understood as the difference between one heartbeat and the entire history of human civilization, repeated millions of times. If life is possible, and we are existence proof that it is, and if the ingredients for life are as common as Webb's atmospheric surveys suggest, and if the time available for life to develop on worlds older than Earth extends to durations that dwarf the entire history of terrestrial biology, then where is everyone? This is the Fermi paradox. It is not new. Enrico Fermi posed it informally at a lunch table in 1950, and it has never been satisfactorily answered. But Webb has made it exponentially more acute, because every image Webb produces, every atmospheric detection, every interstellar molecular cloud mapped in the infrared, adds to the abundance on one side of the equation, the side that says life should be common, without adding a single signal, a single artifact, a single unambiguous trace of intelligence to the other side. The universe Webb is showing us is not empty in its chemistry or its structures. It is empty, with terrifying consistency, in its communications. The silence is not the silence of a place no one has ever been. It is the silence of a place where, statistically, someone should have arrived long before you and left a mark. And there is no mark. Across the entire electromagnetic spectrum, through every receiver humanity has pointed at the sky, through every optical survey and radio telescope, and now through the most sensitive infrared observatory ever built. Nothing, no structured signal, no repeating pattern that exceeds what physics alone can produce, no megastructure orbiting a distant star in a configuration that defies natural explanation. No Dyson sphere dimming a stellar light curve in the precise way an energy-harvesting structure would. Some solutions to the Fermi paradox are technical. Perhaps interstellar communication is harder than we think, and civilizations do not transmit in the bands we search. Perhaps the galaxy is so large that signals take millions of years to cross it, and we are simply too young to have received anything yet. Perhaps life, even when it begins, rarely produces intelligence, and intelligence rarely produces technology, and technology rarely survives long enough to become detectable. Perhaps we are genuinely among the first, an early flowering in a cosmos that will bloom with intelligence in another 10 billion years, when we are long gone and unable to witness it. But there is another class of solutions, darker and more difficult to dismiss. The Great Filter. The idea, proposed by economist Robin Hanson, that somewhere in the sequence of steps from simple chemistry to spacefaring civilization, there lies a barrier so formidable that virtually no lineage ever crosses it. A filter so effective that the universe is functionally sterile at the level of detectable, expansive intelligence, despite being chemically and physically primed for life at every scale Webb can observe. The question the Great Filter poses is not whether the filter exists. The question is where it is, behind us or ahead of us. If the filter is behind us, if the great bottleneck was something in our evolutionary past, some extraordinarily improbable step that our lineage somehow navigated, then the silence makes sense. We made it through a gauntlet that almost nothing else survived. We are perhaps genuinely rare, genuinely exceptional in a cosmos otherwise full of dead chemistry. And if that is true, then our existence is not typical. It is a statistical miracle, a thing that should not have happened and yet did against odds so long that they approach the boundary of impossibility. If the filter is ahead of us, if the great bottleneck lies not in the development of intelligence but in its survival, then the silence carries a different weight entirely. It is not the silence of empty origins. It is the silence of termination. It is the sound of every civilization that got this far eventually reaching something it could not endure. A technology, a miscalculation, a physical or social or biological threshold from which no lineage ever returns. And if that is the case, then the fact that the universe is full of ancient stars and old worlds and the chemistry of life, and yet contains no detectable trace of persistent intelligence, is not a puzzling cosmic statistic. It is a warning. Webb cannot resolve the Fermi paradox. No telescope can. But what Webb is doing, by quantifying the abundance and antiquity of potentially habitable worlds with unprecedented precision, is making the paradox sharper. The more habitable worlds it finds, the more the absence of detectable life demands explanation. The more ancient the galaxies it reveals, the more time has been available for intelligence to emerge and leave its mark. And the more precisely Webb maps the chemistry of exoplanetary atmospheres, the closer we approach the moment when either we detect a biosignature, a chemical imbalance that only biology could maintain, or we confirm that world after world after world cycles through chemistry without ever producing what Earth produced. That moment has not yet arrived. The biosignature search is ongoing. Webb has the capability to detect oxygen, methane, ozone, nitrous oxide, the gases that life on Earth has been pumping into the atmosphere for billions of years, in the atmospheres of planets around nearby stars. This is not theoretical. It is a program of observation already underway. If life is common, Webb has a reasonable chance of seeing its chemical signature within the next decade. If it sees nothing, if world after world of habitable, ancient, chemistry-rich planets shows only the sterile signatures of geology and photochemistry, that absence will be a discovery as profound as any detection could be. The universe Webb is mapping has one more dimension that no map can fully capture: time's arrow. The cosmos is not static. The expansion that Webb measures in its most distant objects is accelerating. Dark energy, whatever it is pushing galaxies apart at an ever-increasing rate. In the far future, the universe will not look like it does today. Galaxies beyond our local group will recede faster than light can close the distance. They will become permanently unreachable and eventually undetectable, their light redshifted beyond any instrument's capacity to catch it. The window Webb is looking through, the window onto the observable universe, the 93 billion light-year sphere of detectable reality, is not fixed. It is closing, not in any timescale that concerns a human life or a civilization or even a geological epoch, but on the cosmological timescale of hundreds of billions of years. The universe visible from any point within it will shrink. The 2 trillion galaxies Webb sees today will, one by one, cross the horizon of accelerating expansion and disappear. Future astronomers, if they exist, will inherit a universe that looks smaller than ours, not because it has contracted, but because more of it will have receded beyond the reach of light. And astronomers living hundreds of billions of years from now, if the universe produces observers that persist that long, will have only the local group of galaxies to observe. They will look out and see almost nothing. They may conclude, with all the instruments available to them, that the universe contains only a small cluster of galaxies, that the cosmos is simple, bounded, intimate. They will be catastrophically wrong, and they will have no way of knowing it. We are fortunate, in a cosmic sense, to exist now. To exist at the moment when the universe is old enough to have produced us, but young enough that the evidence of its full extent is still within reach. Webb is the instrument of this particular unrepeatable window. It is humanity's eye at the keyhole of a door that time is slowly, irrevocably closing. Whatever Webb finds in the decades ahead, whether it confirms the Standard Model's foundations or continues to fracture them, whether it detects a biosignature or deepens the silence, whether it resolves the Hubble tension or reveals a cosmos so complex that a single constant cannot describe its expansion, it will find it in the brief cosmic interval during which such things can still be found. After that interval closes, the universe will hide itself again. The darkness will return. Not the darkness of the cosmic dark ages, lit eventually by the first stars. A different darkness. The darkness of a universe that has spread itself so thin, across so many billions of light years of accelerating void, that even the light cannot keep pace with the separation. What we are doing now with Webb is reading a letter that will not remain legible forever. The universe is writing it in light. We built a mirror fine enough to receive it. And in the words of that letter, in the spectra of impossible galaxies and the atmospheric chemistry of distant worlds, and the tension between 2 ways of measuring a universe that refuses to measure consistently, we are encountering something that demands not just scientific revision, but a reckoning with what it means to know. what it means to be the kind of being that asks questions about where it came from and how large the place it inhabits truly is. Because the universe is not indifferent to those questions. It simply answers them in a language larger than the one we came equipped to speak. There is a photograph that no one has taken yet, but that everyone who has looked at Webb's images has already imagined. It is not an image of a galaxy, not a nebula, not a black hole, not a planet wreathed in cloud. It is a photograph of the edge, of the absolute limit of what any light-gathering instrument built by human hands could ever perceive. A photograph not of something, but of the boundary beyond which all things become invisible, the cosmic horizon, the last photon, the final moment before the universe goes silent, not because it ends, but because space has carried its contents beyond any possible reach. That photograph does not exist and cannot exist. The cosmic horizon is not a surface you can image. It is a condition, the condition of expansion exceeding access, of space outpacing light, of distance becoming permanent in a cosmos that was never obligated to stay within our grasp. And yet Webb, with every observation it makes, is pressing its golden mirrors as close to that limit as the physics of this universe allows. It is not reaching the edge, but it is reaching toward it with more precision, more sensitivity, more resolved clarity than anything humanity has ever pointed at the dark. What does it mean to press against the edge of the knowable? Science has a practical answer. It means collecting photons, running statistics, publishing results, building better models, testing predictions, revising assumptions. It means the meticulous, patient, collaborative work of thousands of people across decades, pooling their lifetimes into instruments capable of asking questions on humanity's behalf. It means the unglamorous, essential labor of calibration and uncertainty, quantification and peer review and replication. It means the standard model of cosmology, imperfect as it now appears, standing as the hard-won accumulation of centuries of human reasoning, from Copernicus removing Earth from the center, to Hubble discovering that the Milky Way is not the universe, to Penzias and Wilson accidentally detecting the echo of the Big Bang in the static of a radio antenna pointed at the sky. Each of those moments felt, to the people who lived through them, like the end of one world and the beginning of another. Each of them contracted the human ego and expanded the human imagination simultaneously. Each of them said, in the clearest possible terms, the universe is not what you thought. The universe is more. And each time, after the disorientation, humanity did not retreat. It leaned in. It built the next instrument. It asked the next question. Webb is that next question, and the question it is asking, the question its data is forcing us to confront, is whether the framework we built to describe the cosmos is adequate for the cosmos that actually exists. Not the cosmos we imagined, not the cosmos our equations predicted, the actual one, the one where galaxies form too early and too massively and too organized, the one where the expansion rate refuses to be a single number, the one where 95% of all the mass and energy that exists is invisible, undetected, unnamed in any satisfying physical sense, known only by its gravitational shadow on the 5% we can actually see. We are, in the most literal sense, mostly blind. The universe we study, the universe we have spent centuries mapping and modeling and measuring, is a thin, luminous film on the surface of something vastly larger and vastly darker that we do not understand. Dark matter, the invisible scaffolding of every galaxy, every cluster, every filament in the cosmic web, present everywhere and detectable nowhere except through its gravitational influence on the matter we can see. Dark energy, the pressure that fills all of space and drives the universe apart, unnamed and unexplained and measured only by its effect on the rate at which galaxies recede. Together, they constitute the overwhelming majority of everything that exists. And we have given them names that begin with the word dark, not because they are sinister or dangerous, but because they are simply beyond our current capacity to illuminate. What Webb is doing, in part, is mapping the shadow. By observing how galaxies cluster, how light bends around invisible masses, how the large-scale structure of the universe deviates from predictions, it is tracing the contours of what cannot be seen directly. It is doing astronomy the way a blind person reads a face, not with eyes, but with the pressure of fingertips on the features of something real, constructing understanding through indirect contact. And in those contours, those indirect traces, anomalies are emerging that suggest the shadow is shaped differently than we thought. That dark matter is not the cold, slow, passively clustering substance our simulations assumed. That dark energy is not the fixed cosmological constant Einstein reluctantly introduced a century ago. There is a possibility, not confirmed, not even the dominant view among cosmologists, but a live possibility, a door that Webb's data has not yet closed, that dark matter and dark energy are not two separate unknowns, but aspects of a single deeper unknown. A field, perhaps, a property of space-time itself, expressing differently at different scales and different epochs. Something that our mathematics have not yet found the right language to describe. The history of physics contains precisely this pattern, two phenomena that appear unrelated until the right framework shows them to be aspects of the same thing. Electricity and magnetism, space and time, mass and energy. What looks like two mysteries from where we stand may be one mystery seen from two angles, and we may simply not yet have rotated far enough to see them coincide. That rotation, that shift of perspective deep enough to reunify the fragmented picture, is what a new theory would provide. It would not erase Webb's anomalies. It would explain them. It would show why the early universe produced those impossible galaxies not as a violation of physics, but as a natural consequence of a physics we had not yet reached. It would reconcile the two Hubble values not by choosing one over the other, but by showing that both are correct measurements of a quantity that is not, in fact, a constant. It would place dark matter and dark energy inside a framework that makes them not mysterious additions to the ledger, but inevitable consequences of deeper principles. That theory does not yet exist. It is being sought. It is being built, piece by speculative piece, in the equations of physicists who are willing to sit with the discomfort that Webb's data has introduced and use it not as a reason for despair, but as a constraint, a new requirement that any future theory of everything must satisfy. Every anomaly Webb finds is not a defeat. It is a clue. It is the universe leaving a breadcrumb, narrow and precise, on the path toward a truth that our current maps do not show. But here, at the end of this journey through Webb's eye and into the structure of the cosmos, there is something that no new theory will resolve, something that will remain true regardless of what physics discovers next, regardless of whether the impossible galaxies are eventually explained, or whether dark energy turns out to be a dynamical field, or whether population 3 stars are finally confirmed, or whether the Hubble tension is resolved by a modification of gravity or an adjustment to inflation. The universe is vastly, overwhelmingly, incomprehensibly larger than the reach of any awareness it has ever produced. You are a temporary arrangement of atoms that the universe spent 13 billion years assembling. Through stellar nucleosynthesis and supernova dispersal and planetary accretion and geological processing and biological evolution and neural complexity, into something capable of asking where it came from and how large the place it inhabits truly is. The asking is not incidental. It is the most remarkable thing in the observable universe. In all of the 2 trillion galaxies Webb can see, in all of the hundreds of billions of stars per galaxy, in all of the potentially habitable worlds orbiting those stars, the only confirmed instance of anything turning light into questions, turning photons into philosophy, is here. Is you. Is this moment in which a mind shaped by 4 billion years of biological trial and error points itself at the dark and refuses to look away. The universe does not need you to understand it. It was expanding before you arrived and will continue expanding long after you are gone. Its galaxies will collide and merge, and their stars will age and die, and the last red dwarfs will cool and darken, and the black holes will slowly evaporate, and the cosmos will arrive at a stillness so total that thermodynamics has a name for it, a name that sounds almost peaceful: heat death. The end not of space, but of difference. The end not of the universe, but of the gradients, the temperatures, the pressures, the concentrations that make events possible. All of that will happen without requiring your witness. The universe is indifferent to being understood. And yet, here you are, understanding it anyway, or trying to, or holding the instruments of that attempt up to the sky and letting the light fall in. Ancient light, light older than the sun, light that crossed the entirety of cosmic time to reach a mirror you built and a mind you brought to bear on its meaning. That is not nothing. In a universe this large and this dark and this silent, the fact that any of it ever became curious about itself is, perhaps, the most staggering fact of all. Webb did not give us the size of the universe. It gave us the honest admission that the size cannot be given, that the border we drew around the knowable is not a wall, but a horizon, and that every horizon, by definition, retreats as you approach it. The universe will always be larger than the light it has had time to send us. It will always exceed our instruments. It will always leave a greater darkness behind what we can see than what we have illuminated. But the reaching matters. The looking matters. The willingness to build a golden mirror and launch it into the cold dark and ask it to tell us what is out there, knowing it will answer not with completion, but with deeper questions. That willingness is what it means to be the kind of thing that the universe, against all probability, somehow became. We are the universe looking at itself, and what it sees through us is how much of itself it has not yet seen.